Next I will explain multiple frequency CW radar, MFCW, multiple frequency CW radar. What is the main drawback of CW radar is it does not measure range, but it is possible you can measure the range by using simple CW radar by measuring the phases of echo signal relative to phase of the transmitted signal. If you provide some means of measuring the relative phase difference between echo signal and transmitted signal by using that phase difference between transmitter signal and echo signal, you can find the range of the radar by using CW radar. So, CW radar does not measure range, but it is possible by measuring the phase of the echo signal relative to the phase of the transmitted signal. So, the principle used in multiple frequency CW radar is the measurement of range by computing the phase difference between the echo signal and transmitted signal. The signal radiated by the transmitter travels to target at a range r and returns to the radar after a time capital T is equal to 2r by c. 2r is the two-way distance between radar and target. C is the velocity of the electromagnetic waves. So by dividing this 2r by c, you can find the total time travelled by the transmitted signal to the target and return to the radar. For example, if we consider a CW radar radiating a single frequency sine wave of the form sine 2 pi f naught t. Here assuming amplitude is 1. So, in this case you have two methods. One is by using single frequency. In that case, find the phase difference between transmitter signal and echo signal. From that you can find range, but in that range you can find the only short ranges. If you want to find longer ranges, we have to use two or more frequencies. I will also explain these two methods. First, this is the transmitted signal. This transmitted signal reaches to the receiver after certain time, this t, that introduces certain phase difference. So this is transmitted signal. Then what about the received signal? If transmitted signal and received signals are compared in phase detector, the output of the phase detector is proportional to the phase difference between two, and that phase difference del phi is equal to 2 pi f naught into t. This is the time taken by the transmitted signal travel to target and return to the echo signal. That time into this omega. Omega into time is phase. So del phi is equal to 2 pi f naught t. Here t is equal to 2r by c. So this del phi is equal to 4 f naught r by c. From this, the phase difference may be used as a measure of the range. So from this, r is equal to c del phi by 4 pi f naught. C by f naught is wavelength, so lambda by 4 pi into del phi. So if you know this phase difference, then you can find range. However, the measurement of phase difference del phi is unambiguous only if del phi does not exceed 2 pi radians. So if this del phi phase difference is less than 2 pi radians, then the range measured is exact range, correct range. If this phase exceeds this 2 pi radians, then this measure range is not correct range. For example, if you substitute del phi is equal to 2 pi in this equation, 2 pi 1s and 2 pi 2s, then r is equal to lambda by 2. So this is the maximum unambiguous range which can be measured by measuring the phase difference between echo signal and transmitted signal. So this is the only half of the wavelength of the transmitted signal, which is very short range. So at radar frequencies this unambiguous range is much too small to be of any practical interest. So this is very small. So how to extend this unambiguous range? By using two different frequencies. That means transmit two different frequency signal towards radar and receive that two different frequency signals, and that received echo signal phases take the difference of phase of the two echo signals. By measuring that phase difference, you can also find range of the radar. Here, the unambiguous range may be extended by considerably by utilizing two separate CW signals differing slightly in frequency, slight frequency variation, not large variation. The unambiguous range in this case corresponds to half wavelength at difference frequency. In previous, half wavelength lambda is corresponding to operating frequency of the transmitted signal, but here we are transmitting two frequencies, different frequency f1 and f2. Take the difference f1 minus f2. For that frequency, calculate wavelength. In that frequency, divided by that corresponding wavelength by half. Then we are getting that wavelength corresponding to difference frequency. If the transmitted waveform is assumed to be consists of two continuous sine waves of frequency f1 and f2. That means v1t is equal to sine of 2 pi f1t plus this is initial phase difference. Similarly, second signal, these two are transmitted, the corresponding echo signals are received, then measure the phase difference of these two echo signals corresponding to these two. Here the echo signal is shifted in frequency by Doppler effect. The form of Doppler shift signal at each of these two frequencies f1 and f2 may be written as this one. If this signal is transmitted, the corresponding echo signal is this one. Next, if this signal is transmitted, the corresponding echo signal is this one. This FD1 is Doppler frequency shift corresponding to f1. This is Doppler frequency shift corresponding to f2. This is the phase difference due to range. This is also phase difference due to range corresponding to f2. This is phase difference due to range corresponding to f1. If these two are given to phase detector, the output of the phase detector is proportional to phase difference of these two signals. And in general, this f1 and f2 are slightly varies, hence these two are equal. Now take the phase difference. Where R0 is the range to the target at particular time t is equal to t0. FD1 is the Doppler frequency shift associated with F1. FD2 is the Doppler frequency shift associated with F2. FD1 is equal to FD2. The receiver separates two components of echo signal and heterodynes each received signal component with corresponding transmitted waveform and extracts the two Doppler frequency components given by this one. This is the extracted signals. If these two are given to phase detector, the phase difference between these two. Why this FDs are equal? FD1 is equal to FD2. There is a little bit phase, very negligible phase, frequency difference between these two. The phase difference between these two components. This two component means this one. The phase difference between these two. These two are cancelled. Then this minus this. Del phi is equal to 4 pi f2 minus f1 R0 by c. Here f2 minus f1 is del f, frequency difference. From this R0 is equal to c del f by 4 pi del f. Here also this del phi does not exceed 2 pi to get unambiguous range. If we substitute this del f is equal to 2 pi, then 2 pi and 4 pi cancel, then we are getting 2. So therefore the maximum unambiguous range or unambiguous is equal to C by 2 del f. This is the maximum unambiguous range. Actually C by f means wavelength. In previous case, in single frequency case, this unambiguous range is lambda by 2. That lambda is corresponding to operating frequency f naught. But here C by del f, this del f is corresponding to frequency difference between two signals. If this difference is very small, then range can be increases. How to increase this unambiguous range? By decreasing the frequency difference between two frequencies f1 and f2. This is way of finding range by using CW radar.